Again, good morning, good afternoon, and good evening, everybody. Welcome to our webinar, Machine Learning 101, Performance Analysis and Demonstrations, a collaboration between NXP and Boundary Devices. I'm your moderator and speaker, Bosco Jung with NXP Semiconductors. Thank you for joining us today. We'll reserve the time for Q&A at the end, so please take a moment now to find the question box on your GoToWebinar user interface. Please submit your questions in the question box at any time, and our speakers will answer as many questions as time permits at the end. We'll have Peter Hawk, the Director of Sales, and Gary Bisson, Software Lead for Machine Learning from Boundary Devices. And I'm from NXP, Business Development and Industrial NPU Partner Manager, speaking today. So without further ado, I'll ask Peter to begin his presentation. Peter.
Good day. Thanks for the introduction, Bosco. We're excited to be here, talk about our Machine Learning 101. Again, I'm Peter Hauck, Director of Sales, and joining me from our software team, our Machine Learning Lead, Gary Bisson. Here you can see our agenda for today, a brief introduction on who Boundary Devices is and what we do, our Nitrogen 8M Plus based Machine Learning 101, NXP's i.MX overview for machine learning, and finally a question and answer. Should you wish to reach out to us after this session, we have included contact information on the last slide. Boundary Devices creates ARM-based SOMs, SBCs, and customs at our headquarters in Lake Forest, California. We are an NXP embedded board solution partner focused on custom i.MX solutions. All products are designed, tested, and manufactured in the US. We are flexible and aggressive, often beating our offshore counterparts. We do this with built-in the US solutions and support. When we say solutions, we're referring to both hardware and operating system level software. Many suppliers say they are flexible, but they don't provide anywhere near the hardware and software configurations we do. With 17 years experience, we can quickly design custom solutions in as little as 12 weeks. For changes to PCBs on a custom SBC or carrier, we have competitive NREs. If you want half the PCB size, battery operated, no expansion slots, no problem. For custom SBC or SOM memory configurations or depopulation, we have small MOQs of 100 and 500 pieces respectively. If you want 4 gigabytes LPDDR4 and 120 gigabytes eMMC, no problem. If you want to depopulate Ethernet, Wi-Fi, Bluetooth, or HDMI, no problem. Industrial or consumer temp, conformal coded, all no problem. If you're designing your own carrier, we provide the Altium design files along with a complimentary schematic and layout review. This flexibility, together with tested BSPs, drivers, and OS maintenance, is included in the price of your board. For smaller quantities, you can buy our off-the-shelf products. For larger quantities, we can cost optimize and give you exactly what you want. I've touched on most of these benefits already, but one deserves special mention. We created the original i.MX 6 reference design, the Sabre Light board for Freescale at the time, now NXP. We've been creating both standard and custom solutions for many years, and experience matters. Along with a seasoned team, we provide longevity of supply, guaranteeing at least 10 years production. We use both internal and external manufacturing depending on the requirements. This provides us with quick turns on customs as well as redundancy in our supply chain. You can save on travel, translation, and delay by working with Boundary Devices. Say goodbye to supply chain issues related to COVID or tariffs. Where we sell anywhere. The United States is our primary market, but we truly sell worldwide. Our leading segments are medical, industrial control, kiosks, access control, and gaming. But it's a long tail of accounts across thousands of applications. We're very proud of our service, support, and contributions to the community over the years. After this webinar, we hope you take the time to explore the Nitrogen 8M Plus in more detail. Now on to the most exciting part of the presentation, the Nitrogen 8M Plus SOM. As an NXP Alpha partner for the i.MX 8M Plus, we already have working SOMs and carriers in-house. We are shipping to first customers today for evaluation based on pre-production silicon. We will be ramping to full production in Q1, but NXP silicon and our SOM look great. Nitrogen 8M Plus adds an NPU, but it also adds a lot of great I/O with 3 display outputs and HDMI up to 4K 30, an onboard ISP, and a Hi-Fi 4 DSP to name just a few. For boundary devices, this is our smallest SOM to date, and for the first time includes a Wi-Fi and Bluetooth option. As you can see, industrial temp and conformal coding are also available. Listed, you can see some pricing along with target applications and operating system supported. Android along with many flavors of Linux are provided, as well as a new addition, Mendel. To see our many software contributions, be sure to check out our wiki and our blog. There are active links on this slide and on all the slides, and you can see those in the handout. In terms of carriers, you can see we will be enabling the SOM with 2 carriers. The first carrier, or EVK, brings out as much I/O as possible for our customers to develop on. This carrier is available today and in stock for select customers. On the documentation tab of the SOM and carrier, you will find the product manual, schematic, and step file. The second carrier will have less I/O and fit into our existing i.MX 8M enclosure listed on our accessories page. Beyond the hardware and software platforms themselves, we also provide a number of accessories. These products are intended to allow our customers to develop a full proof of concept. After evaluation, we can then work with the customer to optimize for production. For the Nitrogen 8M Plus, we have displays, a camera kit based on Basler, cellular based on Quectel, HDMI and PCIe adapters, and an enclosure. Lastly, we have a display integration service. Customers can prototype with our displays and then move to a production display of their choosing. We will create the little PCB prototype daughter board and cabling required to interface to a Nitrogen board. This includes LCD timing setup and touch controller integration into our BSPs. At the end of the day, we create boards bundled with software to get you to market quickly. That is our core business. Summarized here is the Nitrogen 8M Plus enablement. You can buy the discrete components or you can buy a kit and save some money. We are accepting orders and shipping today. Lead time will vary based on demand. Thank you for your time, and now on with Machine Learning 101 with Gary.
All right, thank you, Peter. Let's now have a look at machine learning, what it is, how it works, and how to get started with it. Before that, a disclaimer is in order. I am not a data scientist. I am a software developer who experienced with the whole process. So I'm here to give you hopefully a good overview of machine learning and answer some of your questions. First, let's take a look at what machine learning is, how different it is from artificial intelligence or deep learning, as those terms are usually used at the same time. Artificial intelligence is a program that solves problems within a known area. It's been around for a while now, and the best example is Deep Blue chess playing computer, which was built from 1985 to 1996. And this program could solve chess games, but it was only meant for that game and only knew the 8x8 square grid, basically. Next evolution is machine learning. It is a subset of AI, and it provides systems the ability to learn and improve from experience. It can be summed up as using data to answer questions. The idea is that from previously collected data, the system tries to see patterns that would help defining some sort of algorithm to solve any problem like that. For instance, voice recognitions require a lot of different voice recordings so that the machine knows about different accents, different speeds of delivery, and so on. And that way, it can pick up and understand any voice, even the one that it hasn't heard before. Finally, Deep learning is a subset and an evolution of machine learning, as it can learn and discover on its own, as it tries to mimic the human brain, basically. Deep learning is obviously requires high-end machines, which is not the topic of today's presentation. So that is why we will focus solely on machine learning. Before getting any further, I wanted to explain a few terms that I will be using throughout this presentation. The most important ones are a model. A model is a representation of what a machine learning system has learned from training data. The training is the process that takes the data and makes it into a model. And that training data is called a data set, which is a collection of features like images, for instance, when you want to do some object detection. And along with that, labels. Those labels are used during the training to help define known answers or known results. A neural network is a model composed of different layers, each layer being itself a set of nodes, input or output, as you can see in the diagram. Models can have many layers, but then it impacts their size and therefore the inference time. Inference time is the time it takes to actually run the model on a specific input. All right, now that we've seen the terminology, you might wonder why everybody is talking about machine learning nowadays. Would it apply to your project? The truth is, there are already like many obvious applications that are already in use today, like voice recognition, face recognition, crowd counting, and so on. But what we see is that many industries are looking at it now to see if it could help perform tasks that weren't automated before. For instance, when making your electronic device, some manufacturers use machine learning to do visual inspection on the platform at the SMT line to make sure that every component is properly placed. So that is a good example of an industrial application, and really the possibilities are limitless. So then the question is, what are the main stages of a machine learning project? Well, first is data collection. Once again, machine learning relies on the data used to train the model. So picking up the right data and the right amount of data is crucial. You need to have a lot of data, as many as you can, and it has to be relevant. The second stage is to pre-process that data. For instance, you might need to sort it so that you can label it so that the training process knows what is a good result or how each component is named and so on. Then you can train your model, which usually doesn't happen on the target, but rather on a powerful computer or even in the cloud. Note that you usually want to split your data set, so that 70 to 80% is used to train the model and the rest is used to test it. That allows you to know how accurate your model is at the end. At this stage, you can evaluate your model in real-life conditions, checking its accuracy with new data. And usually, the final step is actually to keep improving your model with new data that you're gathering so that it gets even more accurate every time and at every iteration. So this workflow applies to any machine learning project. But note that in our case, the model will run on the target itself. That is what we're interested in, and that is what we call running at the edge. It's the opposite concept of doing some cloud computing that requires to send the data to a cloud service in order to have your prediction. There are many advantages when using edge computing, like data protection, as the data doesn't leave your device, faster computation, as it's not dependent on the network, it doesn't send anything and doesn't wait for the network to answer. And finally, it is a much more resilient approach, as it means no dependency to any cloud service. The perfect example happened last week, actually, with a famous data center failure, which resulted in many IoT devices not functioning at all. Like you can see this person complaining that he can't vacuum since the server is down. So that is exactly what we are trying to avoid here. Now, how to get started with machine learning? Well, there are many resources available online ready to help you. There are different inference engine or frameworks like Tensorflow Lite or RMNN. They are here to ease your life. Along with those frameworks come some ready-to-use models. So all the links will be provided in the slides. Same goes for all the different types of models, whether you want to use MobileNet, Inception, FaceNet. Note that each model type has its own trade-offs. It's actually depending on the type of application you're looking for, whether it is classification, detection, and so on. Same goes for the dataset. You can get some image dataset for free on websites like ImageNet, Kaggle, or TensorFlow datasets. But on top of those generic machine learning resources, NXP provides the EIQ software environment for its i.MX family of processors. It supports all the industry-leading frameworks like TensorFlow and RMNN, like we discussed before. And each framework is optimized for the i.MX, whether it uses the neural processing unit in the case of the i.MX NM Plus, or the GPU on some others processors like the i.MX NM Quad. The EIQ software environment comes with plenty of examples as well, which we will see in the first demo. The different frameworks also provide their fair share of examples, like TensorFlow Lite, which will be the main focus of this presentation. EIQ is for Linux distribution, but Android also provides an accelerated API with its neural network hardware abstraction layer. As you can see in the diagram on the right, no matter the user space framework or library that you use, it all comes down to the OpenVX library, which will be in charge of running your machine learning code, whether in the GPU or the NPU. And another option which is worth mentioning is Mendel Linux, which is a Debian-based distribution made by Google, especially tailored for machine learning with their HTPU devices. Okay, so we've talked about machine learning and what it is, how to get started. Now let's see what kind of performances we can get out of it. For that, we're going to compare two different solutions from boundary devices. Our first solution is based on the Nitrogen RM, which uses the i.MX NM Quad processor from NXP. It includes a quad-core Cortex-A53 running at 1.5 GHz, along with a GC7000 Lite GPU from Vivente. There are many video features like 4K 60 output and decoding, but there is no neural network processing unit. So to do that, we will use the Google Edge TPU machine learning accelerator in its mini PCIe form factor that you can see on the right. This TPU provides 4 tera operations per second, also said TOPS, with integrated power management. We will use Mendel Linux for the performance analysis testing. The other solution is what Peter talked about, which is our brand new i.MX NM Plus based system on module called the Nitrogen LMP. This CPU also offers 4 Cortex-A53 cores, this time running at 1.8 GHz, along with a smaller 3D GPU, but with another 2D GPU. The main addition here is that it is the first i.MX product to integrate a neural processing unit capable of delivering 2.3 TOPS. There are other noteworthy features like the ISP for vision and 3 display outputs and video decoding and encoding. This system on module already supports Yocto, Debian, and Android, and other distributions are on their way. Before we get any further, there are some hardware consideration and limitation which I think are important to mention, which they both apply to the NPU and the TPU. First, you need to make sure the model that you're running is optimized for your hardware. So both TPU and NPU require the model to be quantized, and moreover in integer 8 to be able to run on them. An 8-bit quantized model means that every operation or weight inside the model are changed from the original float32 type to the integer 8 type. That means the model is 4 times smaller and runs faster, but there is also a loss, and you have to make sure that you know about that change when you train the model. Because if you use an operation that is not supported by the NPU or TPU natively, it will either be converted on the fly or fall back on the CPU, which greatly impact the performances. The second thing to be noted is that they both have warm-up time. It is normal considering that the model needs to be loaded to a place in memory where the processing unit can access it as fast as possible. And this only happens once when you load the application. Any subsequent run of the same application will give you quick response time. So you can see the table at the bottom that gives you some warm-up time for the NPU. Considering the previous slides, it is worth saying that among the many models or examples you will find online, not all of them will be matching the required quantization for your platform. Even sometimes the model is named model_quantized.tflite, but yet inputs or output are still in float32, which once again means that it will fall back to the CPU and give you poor performances. So fortunately, there are some tools available for you to analyze model binaries and get that information from it. So I have provided here links to 2 different options, the Google Flat Buffer project or the Tensorflow Lite analyzer. Both of them will give you every information about every weight inside your model, so you know what type is expected, and that would explain why it is running poorly or not on your device. Note that you can do some post-training quantization to transform basically a non-quantized model to quantized. But for that, you'll need some representative data to do so. So basically, it's best if you have your own data set to do that. Regarding the setup, ideally, we would have used the exact same image to compare both options, but it happened to be pretty complicated. So we decided to focus on using the same kind of simple Python application for each platform using the exact same input image, exact same model, and labels. The reason for that difference is that the Edge TPU doesn't use the standard neural networks library, but instead its own libEdge TPU that requires to modify every Python interpreter to be used by default. So we basically use the Tensorflow Lite classification and detection sample app, as well as their equivalent for the Edge TPU by using the PyCrawl API. Unfortunately, the Tensorflow Lite benchmark application couldn't be run on the TPU, but we still ran it on the CPU just to show the difference between both platforms, as once again, sometimes your model might fall back to the CPU anyway. And finally, the result that we're going to show, you don't have to take our word for it. We provide a benchmark package which will allow you to run it on your own, as it provides all the tools, the models, the label, and the images that we used, as well as the comments that we entered. So here's how the result that we saw when running those tests. Those were averages values after several runs. The first 2 lines show that the i.MX LM Plus provide better CPU computation. That makes sense because its Cortex cores run at 1.8 gigahertz instead of the 1.5 of the i.MX LM Quad, so there is no surprise there. Then you can see that both classification and detection numbers are in favor of the i.MX Plus, which is good news. But that is a little bit surprising considering that the TPU is announced at 4 TOPS, whereas the NPU is announced only at 2.3 TOPS. But know that those top figures are provided by the manufacturers in the best environment possible with highly optimized models. Here, we have been using standard pre-built models, the same one in both cases, and that they might need some little more massaging for the HTPU to perform better. Yet, we believe it gives you a good idea of the overall capabilities of both platforms. Also, it shows the benefit of using NPU or TPU instead of the CPU for such processing, as it is much faster. So now let's have a look at demos running on our boundary devices, the Nitrogen NMP platform. The first one can be considered as an out-of-the-box experience with the EIQ software environment. The hardware setup is pretty simple. You can see the Nitrogen NMP at the bottom, a standard 1080p HDMI display, and a USB camera input, as well as the Pi EIQ framework. Software-wise, it's also very simple. It uses the Yocto Zeus OS release from NXP, which includes the EIQ software again. And all the EIQ examples are nicely documented on the EIQ website. We invite you to have a look to discover all of those different applications and how to run them. Finally, the image used for that demonstration is also available on our website, so you can try it right away. So here is the video. So here you see the Nitrogen NM Plus, and the first test that we're gonna do is called the switch video, switch detection. In that case, we feed a video file that you see right now in the inference engine, which is Tensorflow Lite. And we want to see the output as object detection. So if we run that same stream inside the inference engine, what we want to see is that real-time object detection in this case should be like as many cars as possible. So here we can see that the application is starting. And as we mentioned before, it takes a little bit of time to load. That is what we talked about, which it is the warm-up time. So here you can see that the model is running and that it takes between 15 to 20 milliseconds to for the model to be run. So the inference time is between 15 to 20 milliseconds. And you can see that many cars are detected. And what is nice about that application is that it allows you to switch between NPU and CPU. And here, when we switch to CPU processing, we can see that the inference time goes up to 250 milliseconds. So it's much higher. So showing the benefits of the NPU, not only to offload the CPU, but also being much faster. Next EIQ example that we're going to run is using the USB camera, so we can see at real time the input and the object detection. So once again, since it's another application and another model, it takes a little bit of time to warm up the NPU. But here it is. Here I am. I'm glad to be detected as a person by the NPU. That's good news. Now, what if we try what I have around me? So here's an Apple. Here is my tiny phone. Then I think I have a remote here. And this is my cup. So we can see that all those objects are not detected properly at first. Sometimes it needs to be separated from other objects. And also, you need to understand that this is just using like the base pre-built model, which hasn't been trained for a specific set of data. So it includes a lot of different detectable objects. And it would need some optimization with more training data to fix those glitches. So that is it for the EIQ out of the box experience. It is now time to show our latest and exciting demo, which is the face mask detection. This year has been special due to COVID, so we wanted to have a demo related to that. It became obvious that an application detecting if someone is wearing a mask or not was a good example. To do that demo, we are going to use the very same bundle Peter mentioned at the beginning of the presentation. It includes our nitrogen NMP, our 7-inch LVDS display, and the 8 megapixel high resolution DA3840 bachelor camera. So quick info on that camera. The DA3840 is a premium 4K color CMOS sensor with great HDR performances. It is capable of streaming 8 megapixel at 30 FPS. And in this example, we will use it as our vision capture device with a resolution of 1080p at 60 FPS. Regarding the software, we will be using Android 10 with this latest release from NXP, which is the 2.5, adapted to our nitrogen NMP platform, which is already available on our website. We chose Android for simplicity, allowing us to leverage the many examples available online, while still using the OpenVX library thanks to the neural network hardware abstraction layer provided by NXP. Tensorflow Lite was once again the inference engine of our choice. Now, here are some details on how we created that video. First, the dataset comes from Prajna Bandari. She created that dataset very cleverly by generating images of people with masks. So basically, she had many pictures of people without masks, and then she used machine learning to detect where the faces were on those pictures and added a picture of a mask on top of those. That allowed to generate pretty big data set without actual picture of people with masks. This has some limitation, so this is not as good as having a proper data set with real pictures of people with masks, but you will see that it gives you a pretty good result. And also it was very fast to generate more than 1,400 pictures. From that data set, Adrian Rosbrook wrote an article explaining how to train the data and create an application to use that model and detect a mask. That application does it in 2 steps. The first one is to detect the face, and the second step is to run the model on that face, so on the cropped picture of that face. We highly recommend reading through that article as it is full of information. Then another developer, Esteban Yuri, used that model and transformed it into Tensorflow Lite format to use it in an Android app. That application is based upon the Tensorflow Lite detection example application. And Esteban's application runs very well, but it has 2 problems for us. The first one is that it doesn't use a quantized model, so computation is done on the CPU. And the second one is the orientation, which could only allow portrait mode. So Boundary Devices created a quantized model from Adrian's dataset and made the app work in landscape. So let's have a look. So here I am without a mask. As you can see, the app detects my face and sees that I'm not wearing any mask. So now let's see when I put a mask. Here, detection works pretty well. And you can see that the prediction percentage is pretty high for the mask use case. Also note that when I move around, we can see the bug tracking my face with a little bit of latency. So I even tried like 2 different type of masks to make sure that it doesn't make any difference. No difference. So here, let's have a look at the setup itself. You can see here that the frame is 1080p. So once again, it comes from that bachelor camera. Then the application crop it to a smaller resolution to be able to do computation faster. And then you can see that by default, that application runs on the CPU. and that the inference time goes from 130 milliseconds to 200 milliseconds. So what we're going to do here is that we're going to enable the NN API of Tensorflow Lite, which will use the NPU. Oh, sorry. Let's go back. So yeah, so here, so let's enable the NPU. Once again, just like you saw in the EIQ example, it takes time to warm up the NPU with that model. But then you can see that now the inference time drops to about 40 to 60 milliseconds, still providing the same kind of prediction, recognizing my mask fairly well. The no mask prediction is not as good, but once again, like this data set would need to be optimized again, but it's still better. And you can see here, thanks to the better inference time, the latency of the box tracking my head is better. So that is it for our demos. We hope you've enjoyed it. Let us know at the end of the presentation if you have any questions. I will now give the control back to Bosco for the i.MX and M+ overview.
All right, thank you, Gary. Let me turn to my section of the slide. So let me talk to you about the 8M+ applications processor, which is inside of the boundary devices board. Before we dive into the processor itself, quickly introducing NXP if you aren't aware. The NXP is a multinational semiconductor company headquartered in Eindhoven, the Netherlands. We have close to 30,000 employees worldwide, and about a third of us are engineers focusing on developing the next generation of technology. We have products that go into automotive, industrial, mobile, smart home, smart city, and communications infrastructures. So you can see the wide ranges of product portfolio that we provide for you guys, whatever that application may be. And many of the fundamental technologies that we offer go across these 6 segments listed here. And just to give you an idea what that range looks like, here is a chart, that kind of eye chart that shows you the product portfolio based on the ARM processors. So it is best to think of our ARM-based processors, microcontrollers, and crossover processors as a continuum. So we provide we provide a very wide range of processors for you guys. And I primarily focus on the application processors, including i.MX and Layerscape. And if you have used the Power Architecture, PowerPC processors, I also manage that too. But the i.MX family spans devices from 1 to 6 CPU cores and integrates multimedia acceleration. And i.MX processors are well suited to the designs with man-machine interfaces, including graphics and voice. And then i.MX RT family bridges the multimedia capabilities of the i.MX processors with the real-time capabilities and lower costs of our microcontrollers. The family has turnkey AI functions such as Alexa voice. And if we draw a circle with the center being at i.MX and the peripheral going around the RT and Layerscape, that's where the AI or ML at the edge really happens. And among these processors, I would like to highlight the i.MX 8M Plus or 8M series. So the i.MX 8M series offers a scalable solutions that touches many market segments. These processors have different flavors that you can choose from. i.MX 8M Quad, Mini, and Nano family are all available now, and they range from a single to quad ARM Cortex A53 cores with integrated GPUs. The Quad family provides advanced audio, voice, 4K video, 3G GPUs, and with OpenCL and broad connectivity options. Moving on to the Mini and Nano. They're pin compatible, so you can scale up or down depending on your needs. Then we have the i.MX 8M Plus family, which is coming soon in Q1 of 2021. That has integrated DSP, GPU, and NPU, which is the start of this webinar today, which is the neural processing unit. These features are intended for ML, vision, and industrial IoT, as well as advanced multimedia. If you're using 8M Mini or Nano today, scaling is much easier because you get the pin-to-pin compatibility in the 14x14 package. If you want to go either to 8M Quad or 8M Plus families, while they are not pin-to-pin compatible, the entire 8M family is software compatible, including the GPU tools. So making the shift may be much easier than switching both hardware and software. So a few more general key points about the 8M Plus applications processor. As I mentioned before, it is targeted towards the ML and vision systems, advanced multimedia, industrial networking, and applications where the high reliability is required. And subsequently, the smart home, smart buildings, retail and city, smart factory, and industrial IoT applications are the target applications. So before we go into more detail about the 8M Plus processor, here's a chart that shows the range of applications across the machine learning spectrum and the ranges of TOPS. And as Gary mentioned, TOPS is shorthand for tera operations per second. We talked about using NPU and TPU comparison, and it is correct that in some cases that Gary showed, NPU performs slightly better. But as he also mentioned, the advice would be that you need to see which performs better in your use case and your model and your application. So a lot of variables are in it. But this chart is more a general guideline that you can use. And you can go from nearly 0 giga operations per second or hundreds of tera operations per second. So when we're talking about the edge, we are typically in 0 to 3 or maybe up to 10 TOPS in a lot of machine learning applications. But I think the most would fall under 5 TOPS. And we think there are generally 4 categories of use cases for machine learning. First one being the computer vision, speech analysis, video and image processing, and sequence analysis, which is like anomaly detection. I will not go line by line, but let's take a look at the top row, computer vision. You can see the complexity of application goes up as you increase the TOPS. You're doing more complex applications, going from a still image to multi-phase recognition of a video stream, or to multi-object surveillance using multiple cameras. So it is not only the inferencing time that is accelerating with increasing TOPS, but it's also the complexity and resolution of the camera, or simply put, the functionality goes up in the computing spectrum as you increase the TOPS. So moving on to talking about the, sorry, it's a little too much. So let's take a look at the processor 8M Plus. On the block diagram, the compute engines are highlighted, which consists of the 2.3 top machine learning accelerator, 4 ARM Cortex A53s, Hi-Fi 4 DSP, and Cortex M7. We embedded the Cortex M7 real-time processor to offload real-time functions and enable lower power consumption when the apps cores are not in use. So the accelerator can be used primarily for machine learning engine in the system, but you could also use the Cortex A53s for the machine learning engine as well in parallel. For example, if you want to do both speech recognition or object detection and multimedia classification that requires high resolution cameras, then you could do the speech or even object detection recognition with the A53 cores, while the NPU takes care of the high resolution input. And Cortex M7 could be also used in parallel as a sensor aggregation or keyword detection. The other features of the processor, to go over quickly, it is also the first i.MX processor to add inline error correcting code on the DDR memory interface. And this supports high reliability and safety certification levels. As a classical multimedia applications processor, it embeds advanced 2D and 3D graphics accelerators and 3 simultaneous display interfaces, H.265 video decode and encode hardware. It can attach up to 2 MIPI CSI cameras in addition to USB 3 and Ethernet connected cameras. The MIPI CSI cameras are supported with on-chip image signal processor to convert image sensor color code outputs and improve the image quality, like scaling, dewarping, and other enhancements that also can be done. The device also embeds PDM microphone inputs for voice applications along with Hi-Fi. Yeah, we talked about Hi-Fi 4. And then the 8M Plus is a welcome addition to the applications that need 2 gigabit Ethernet controllers with audio, video bridging, or on-time or time-sensitive networking (TSN) support, as well as the CAN FD interfaces and high-speed USB 3 and PCI Express connectivity. So talking about the NPU block within 8M Plus applications processor, first of all, there's a matrix multiply array, which allows you to process models that are built on 8 and 16-bit integer, multiply accumulate functions for tensor operations. It also contains a DMA engine that has compression and decompression, which allows you to store your model weights and your parameters and system memory in a compressed format, and automatically on the fly, when you bring it in, it decompresses. This reduces the bandwidth between the NPU and the system DRAM. Then there's also a specialized neural network hardware that supports functions like activation and pulling. And at the top, if you see on the top left corner, there's a controller which is like the scheduler for all the activities inside of this NPU. And it also is a piece that interfaces with the machine, the main Cortex A53s as it dispatches and commands to this NPU. So quickly on how you can deploy the machine learning onto your platform, as you've seen. So in the end-to-end machine learning, you will always start with model development and do optimization afterwards, or you can do them in parallel. Then you will have the model deployment, which is integration of your model as an inference engine onto the platform or processor. So that's the flow that you're seeing here. You can deploy this on a Cortex-M, DSP, Cortex-A, GPU, or ML accelerator. And these are all compute engines that are inside of different NXP processors. The point here is that it is flexible to deploy your model onto compute engines using convergent tools, say into Tensorflow Lite. Then you can scale it to deploy it on different compute engines because it all takes the Tensorflow Lite format. And you can also convert it to ARM&N, Onyx, OpenCV, or Glow. So that's been it. So I welcome you to visit our website, nxp.com/i.MX 8M+. And thank you for listening in. And whether you are interested in doing chips down design or design yours with a ready-made solution from Boundary Devices, you're in good hands. Please let us know if you can help with your development needs, and don't hesitate to reach out to us. And before we open up the floor for a Q&A session, I have 3 quick polls to ask you guys. First of all, did the presentation material meet your expectations? Hopefully we're seeing positive answers. I will give a few seconds to gather some input. All right, the answers are coming in. A few more seconds. I know a lot of you out there, so appreciate your feedback on this. Okay, so I'll close the poll now, and here's what you have answered. Most of you agreed that the content that we delivered meets your expectation. It's good to hear. And thank you so much for who have participated. Second question, how likely are you to use i.MX 8M Plus in your next project? We're seeing answers coming in, and I will show the results. But at the time, I'm seeing a few folks saying need to learn more. So I'm hoping to get more responses from you or questions that we need to answer during the Q&A session. If the time runs out, we're more than happy to answer your questions later in a separate thread. Okay. Thank you. I'll close this poll. And interestingly, there are a few of you that said definitely not. So maybe maybe you're happy with your current solution. But if you have any further feedback on why you chose definitely not, we'll be happy to hear that. Last but not least, it's asking whether you're doing your own design or going to be using embedded board like solution from Boundary Devices to get started. And if you're undecided, that's fine. And you might be looking to do some hybrid. And Boundary Devices and NXP will work together to cater to your needs and really satisfy what you're looking for. All right, so we got a few more. Give a few more seconds. All righty, I'll close this one out here and show you what the results are. Most of you said you are interested in embedded board design. That's good to hear that we are speaking with Boundary today. 26% of you said undecided. I'm interested in hearing why. Maybe we can help you decide between chips down versus embedded board. And we can definitely have deeper discussions. Please feel free to reach out to us. All right, so to the Q&A session, we have a few questions coming in. The first one, I think it goes to both us and Boundary. What is the recommended inference engine to use? TensorFlow, ARM&N, Caffe, etc. A lot of times we've shown a lot of demos on TensorFlow Lite, as you saw in one of my slides. ARM&N is supported, but I think I can open up the microphone for Gary and give us your feedback as well, Gary.
Yeah, well, it's all a question of traction, and the traction that we've seen so far has been on TensorFlow Lite, so that's why we've focused on that so far. And also, thanks to that traction, that's also what gives you the most examples and the most resources online. Like the documentation on TensorFlow Lite is great, and so on. There are a lot of people using it and providing examples and how-tos and stuff like that. So that is why we decided to go along with that choice. But definitely ARM&N is also supported, and it'd be interesting to see if there is some traction there as well.
Okay, great. The second question, could you compare TensorFlow Lite and TinyML? Are they comparable?
Well, I don't have a good answer for that. But the thing is, here we're especially interested in using the NPU of the i.MX and M+. And so far, what is the different inference engines that are optimized for that NPU are TensorFlow Lite and ARM&N. So I would recommend using either of those for the NPU.
Okay. The next question, what would be the trade-offs with trying to use TensorFlow as opposed to using TensorFlow Lite in the embedded project?
Well, TensorFlow won't run on the NPU. That's the thing. Only TensorFlow Lite is supported, so that would be the trade-off. But then, depending on what you're trying to do, maybe you want to run a TensorFlow model on the CPU. It's just that it won't leverage the NPU, which is meant for that.
Mm-hmm. Thank you. The next question, is there any major trade-offs in choosing i.MX i.MX Mini over a Plus for non-real-time CV application? I think I can answer that question. The i.MX Mini doesn't have inbuilt ISP, so you will need camera with external ISP. We share a 3D GPU only, so it means we don't support OpenCL and cannot run soft ISP or ML on GPU with that. The next question: if I place an order for the
if I may, Bosco.
Yeah, sure.
I would also add that the multiple displays output of the NM Plus is also a big advantage over the Mini, which only has a MIPI output. And we've seen a lot of traction of people wanting to use 2 or 3 displays. So I just want to put it out there.
Great point. Thank you. So if I place an order for the nitrogen 8M Plus kit or EVK, when will I get it?
I guess that question's for me. That'll ship before Christmas. So we're hoping to have it to you in time for Christmas.
That's great. So the next question, why did you decide to support Mendel Linux?
Well, because we've had requests for the HTPU, and so it made sense to adapt Mendel Linux to our platform to be able to use the HTPU. And it seems to be that there is also a lot of traction there. Many customers like the Mendel Linux. Basically, it's Debian. It's a Debian distribution. So if you like Debian, you're gonna like Mendel distribution. And one advantage is that it provides some tools like the MDT tools, which is, if you're aware of Android, which is a bit like ADB. So that allows you to access and debug your application and access your target over USB. So that is what the interest comes from.
Great. One quick question, I think we can answer 2 more. Is it possible to implement PyTorch on NXP NPU? So I can take that. We currently support PyTorch running on the CPU. Currently, we don't have plan to enable it on NPU. So hopefully that answers your question. One last question for you guys. Will the face detection of application be freely available?
Yeah, the APK is downloadable on our website. We're gonna send the link to anyone asking for it. We won't be able to provide all the scripts used to train the model because it comes from the Adrian Rosbrook article, which isn't free, so we cannot take away his work. But the rest of the application will be provided as binaries.
Okay. Yeah, we got 1 more minute. So, and there's 1 more question that I guess we can get to. What's the possible ways, if need to convert the pre-trained models from third-party vendors onto 8M Plus NPU? What about TPU?
Yeah, well, it's going to be the same. What we've experienced with is with the TensorFlow Lite, like converting to a TensorFlow Lite model. You can do that on an already existing model. As I said, the key thing here is that if you want to quantize the model, you're going to need some representative data set. So that means that it's better if you have the origin data set that was used for creating the model in the first place. So it's still doable otherwise, but it's better to have the original data set so that the quantization steps is more accurate.
All right, great. Yeah, we're right at the top of the hour. I appreciate all the attendees for listening in, asking questions. These are very helpful for us. Please don't hesitate to reach out to me in the email they received, bosco.jung@nxp.com, or one of these emails that you see on the screen, either to Peter or info@boundarydevices.com. I appreciate your time and hope you see you in the next one. Bye.